Welcome to the Deep Dive. We sift through your sources, find those key insights, and connect the dots. And today, we're diving deep into the foundations of our world, chemistry. Seriously, think about it. When you start your car, do you ever really consider the chemistry happening? Probably not, right? But it's everywhere. The battery, the fuel, the AC, even the ozone layer way up there. It's all chemistry.
It really is. And not just in the car. It's happening in you right now. Your brain working, the energy from your lunch. Look around, trees growing. That's chemistry too. And you know, that feeling, that special chemistry with someone, that's literally brain chemicals changing. Insects even use chemicals, pheromones to communicate. It's kind of amazing. It makes you wonder what else is going on chemically.
Totally. And that's our mission here, really. To lay out these chemical foundations from your materials. We'll guide you through the big ideas, the core stuff, without making it overwhelming. The goal is for you to see the world, well, chemically. Okay, let's get started. Understanding the microscopic world, the why of chemistry. So people have wondered forever, right? What is stuff actually made of, this whole atomic theory idea? But what's wild is that now, well, for a few decades anyway, we can actually see atoms. Sort of. With this thing called a scanning tunneling microscope, the STM, developed back in the 80s. It uses this incredibly sharp tip, just atoms wide, and it scans across a surface.
And it detects these tiny changes in electrical current as it gets super close. It's like it's feeling the atoms. It really bridges the gap, doesn't it?
Between
our world, the macroscopic stuff we see, cars, beaches.
Yes, a big picture.
And the microscopic world, atoms, molecules. Invisible, but totally real. Think about that beach analogy. From far off, it looks continuous, just sand. But get close, and you see the grains. And those grains, they're made of atoms, silicon, and oxygen mostly.
Right.
And here's the kicker. There are only about 100 different kinds of atoms. That's it. But arrange them differently. And you get, well, everything. Like letters in an alphabet making infinite words.
That alphabet idea really works. It shows how these basic letters build everything. And the arrangement is key. Like water, H2O. 2 hydrogens, 1 oxygen. Simple. But think back to that car battery example you mentioned. If you jumpstart it wrong.
Oh, yeah, that's a powerful illustration.
The electricity can break water down into hydrogen gas and oxygen gas. And if there's a spark, boom, an explosion. And what do you get? Water again.
Exactly. See, that explosion, dramatic as it is, shows 2 fundamental things. 1, matter is made of atoms, different kinds. 2, substances change when you just rearrange how those atoms are connected. That's basically chemistry in a nutshell. Those 2 ideas are core. The scientist's blueprint, the scientific method.
You know, this whole scientific method thing, it sounds formal, but we kind of do it all the time. Like, your phone's dying fast. What's the first thing you do? You notice it, right? That's observation.
Yeah.
Then you guess why. Maybe the charger's shot. Or is it some app? That's your hypothesis. And then you test it. Try a different charger. Close some apps. That's experimenting. It's problem solving, really.
It absolutely is.
Yeah.
It's just a structured way to figure things out. Formally, yeah, we'd say with the observations, could be qualitative, the liquid turned blue, or quantitative, it boils at 100 degrees Celsius. Needs a number and a unit.
Right, the measurement.
Then you formulate a hypothesis, a possible explanation, like maybe substance X caused the color change. And critically, it has to be testable. So you perform experiments to see if it holds up.
Okay, so you test the hypothesis. If it keeps working out, experiment after experiment, what happens then? Does it become a fact?
Good question. It doesn't just become fact. When a hypothesis survives a lot of testing, it can become part of a theory. A theory, sometimes called a model, is like the overarching explanation for why something happens. But, and this is really important, theories are human constructs. They're our best explanations right now. They can always change. New data comes along, we refine the theory, or sometimes even throw it out.
So how is that different from a natural law? I hear that term too.
Yeah. Key difference. A law summarizes what we observe happening. It describes the behavior. Like the law of conservation of mass, mass isn't created or destroyed in a reaction. It tells you what happens. The theory tries to explain why mass is conserved, maybe based on atoms rearranging. So laws describe, theories explain.
Got it. Laws describe, theories explain, and theories can change.
Exactly. Which leads to this idea of human limitations in science. Scientists aren't robots, right? We have biases. We can misinterpret things. Sometimes people get really attached to their pet theories. And outside factors matter too. Funding, politics, beliefs. Think Galileo or Lavoisier back in the French Revolution.
That's a sobering reminder. Science is done by people.
It is. But sometimes amazing things happen anyway, almost by accident, like Post-it notes.
Oh, I love this story.
Yeah. Dr. Spencer Silver at 3M, back in '68, creates this weird glue. It stuck, but you could peel it off easily. Didn't seem very useful.
A failed experiment, kind of.
Well, it didn't have a purpose yet. Then years later, Art Fry, another guy at 3M, is singing in his church choir, and his bookmark keeps falling out of the hymn book. Annoying, right? Suddenly, he remembers Silver's weak glue, puts it on his bookmark, and the Post-it note is barn.
Just needed the right problem.
Exactly. Serendipity. Show science isn't always linear. Solutions can pop up before you even know the problem, speaking the language of science. Units and measurement uncertainty.
That Post-it story is great. It really shows how innovation works sometimes. But okay, back to the nuts and bolts. To communicate science, you absolutely need units. Every measurement, every number needs a label, right? A number alone is meaningless. And we need standards. That's why the scientific world uses the SI units, the international system. It's metric.
Right. It's the universal language for science. Avoids confusion. The basic SI units you run into a lot are the kilogram for mass, the meter for length, the second for time, Kelvin for temperature. And we use prefixes to handle really big or small numbers easily, like kilo for thousand, milli for thousandth, much neater.
Makes sense. And some units are built from others, right? Like volume. It's not fundamental. It's derived from length. Like a cube that's 10 centimeters on each side, that's a liter.
Well, close.
Yeah.
A cube 1 decimeter that's 10 centimeters on each side is 1 cubic decimeter, which we call 1 liter, L. And since a decimeter is 10 centimeters, that cube is 10 centimeters by 10 centimeters by 10 centimeters, which is 1,000 cubic centimeters. So 1 liter is 1,000 cubic centimeters. And 1 cubic centimeter is exactly the same as 1 milliliter, ml.
Okay. 1 L equals 1,000 centimeters bores 1,000 LL. Seeing how they relate helps.
Definitely. And while we're defining terms, let's quickly clarify mass versus weight. They aren't the same. Mass is how much stuff is in an object, its resistance to moving. It's constant. Your mass is the same on Earth or the moon. Weight is the force of gravity on that mass, so your weight changes depending on gravity. You weigh less on the moon.
Right. Mass is inherent, weight depends on where you are. And getting these units wrong, it can be disastrous. Remember the Mars Climate Orbiter?
Oh, absolutely. A classic tragic example.
This hugely expensive spacecraft lost. Why? Because one engineering team used English units, pounds of force, and the NASA team expected metric units, newtons.
The conversion wasn't made. So the thruster firings were calculated wrong. The orbiter went way too low into the Mars atmosphere.
And just burned up. A $125 million mistake over unit conversion.
Wow. Shows why paying attention to units is critical.
It really does. And it connects to the idea of uncertainty in measurement. Look, no measurement is ever perfectly exact. Your instrument has limits. When we write down a measurement, we include all the digits we're sure of, plus one estimated digit. That last one is uncertain. These reliably known digits are the significant figures. They tell you how precise the measurement actually is.
Okay, so sig figs communicate precision. And that relates to accuracy versus precision, right?
Wait,
Sounds similar.
They do, but they mean different things. Precision is about reproducibility. If you measure something multiple times, how close are the results to each other? Accuracy is about how close your measurement is to the true value. The dartboard analogy. If your darts all hit the same spot, that's precise. If that spot is the bullseye, it's also accurate. But if they're all clustered way off in a corner,
then it's precise, but not accurate.
Exactly. And this helps us think about errors. Random errors are statistical fluctuations, sometimes a bit high, sometimes a bit low, usually from estimating that last digit. Systematic errors are different. They consistently push your measurements in one direction, always too high or always too low. Maybe your scale isn't zeroed correctly.
So high precision is good, but it doesn't guarantee accuracy if there's a systematic error lurking somewhere.
Precisely. You could be consistently wrong. The rules of engagement. Significant figures and calculations. Okay, so we know measurements have uncertainty reported with significant figures. How does that affect calculations? You can't magically get more precise just by doing math. Your result is limited by your least precise measurement. So for multiplication and division, the rule is simple. Your answer should have the same number of significant figures as the input number with the fewest sig figs. Okay, fewest sig figs for multiplying or dividing. What about adding or subtracting?
That's different. For addition and subtraction, you look at the decimal places. Your answer should have the same number of decimal places as the input number with the fewest decimal places.
Decimal places for adding, subtracting, sig figs for multiplying, dividing. Got it. And rounding. I know you shouldn't round too early in a multi-step calculation.
Definitely not. Carry extra digits through all the intermediate steps, only round at the very end. And when you do round, you only look at the first digit you're dropping. If it's 5 or greater, round up the last digit you're keeping. If it's less than 5, just drop it.
Right. So 4.348 rounds to 4.3, not 4.4, because you only look at the 4.
Correct. The 8 doesn't make you round the 4 up first. And the practical lesson here, if you're doing an experiment with multiple measurements, try to make them similarly precise. No point measuring one thing to 5 decimal places if another measurement you need only has 2 sig figs total. That less precise one will limit your final answer anyway.
Dimensional analysis?
This all ties into systematic problem solving, which is useful everywhere, not just chemistry. You always need to ask, okay, what's my goal? What information do I have? And crucially, how do I get from here to there?
Absolutely. And for converting units, which is a huge part of chemical problem solving, the best tool is dimensional analysis. Some call it the unit factor method. It's all about using equivalence statements. Like, we know 1 inch equals 2.54 centimeters.
Okay.
From that, you can make two fractions, two unit factors, 2.54 centimeters, 1 inch, or 1 inch, 2.54 centimeters, both equal 1, essentially. You choose the factor that lets you cancel the units you don't want and leaves you with the units you do want.
Let's try one. Say a pencil is 7.0 inches long. Convert to centimeters, you start with 7.0 inches. You want centimeters, so you multiply by 2.54 centimeters, 1 inch.
Perfect. What happens to the units?
The inches on top cancels with the inches on the bottom. You're left with centimeters.
Yeah.
So 7.0 times 2.54 is 17.8 centimeters. The units guide the calculation.
That's the beauty of it. It works for multi-step conversions, too.
Yeah.
Just string the unit factors together. Map out your path first. The final check is always, did the units cancel correctly? Do I have the units I wanted?
Dimensional analysis. Super useful. Heating things up, understanding temperature scales.
All right, let's talk temperature. We typically use 3 scales: Celsius, degrees C, Kelvin, K, and Fahrenheit, degrees. In science, it's mostly Celsius and Kelvin. Fahrenheit is common in, say, the US for daily weather.
Right. And Celsius and Kelvin are closely related, aren't they? Same size degree.
Exactly. A change of 1 degree Celsius is a change of 1 Kelvin. The difference is the 0 point. Kelvin starts at absolute 0, the theoretical lowest possible temperature. Celsius sets its 0 point at water's freezing point. So to get from Celsius to Kelvin, you just add 273.15. TK equals TC plus 273.15.
And Kelvin doesn't use the little degree symbol, just K.
Correct. Fahrenheit. That conversion is a bit trickier, different 0 point and different degree sizes. Water freezes at 0 degrees C but 32 degrees Fahrenheit. It boils at 100 degrees C but 212 degrees Fahrenheit. That's a 100-degree range in Celsius versus 180 degrees in Fahrenheit.
Ah, so the degrees aren't the same size. That's the 95 ratio you see in the conversion formulas.
Precisely. You have to adjust for the different 0 point, the 32-degree Sekrev difference, and the different degree sizes, the 180-100 or 95 ratio.
This really drives home the point.
Yeah.
Don't just memorize the formulas. If you understand why you're adding 32 or multiplying by 95, you actually get it. It sticks.
That's the best way to learn it. Understand the relationship between the scales. Oh, and fun fact, negative 40 degrees Celsius is exactly the same temperature as negative 40 degrees Fahrenheit, the 1 point they cross.
Huh. Good trivia.
Density.
Okay. Another key property, density. Chemists use this a lot, right? To identify stuff.
Definitely. Density is just the mass of a substance divided by its volume, mass per unit volume. Every pure substance has a characteristic density under specific conditions, like temperature and pressure, so it's like a fingerprint.
How do you measure it, typically?
Usually you weigh a precisely known volume of the substance. Pretty straightforward, but you need accurate measurements of both mass and volume.
And this isn't just lab stuff. It's used in real life, too, like you mentioned with car batteries.
Right. The density of the sulfuric acid solution in a lead-acid battery changes as it discharges. So measuring the density tells you the charge level. Same idea for checking antifreeze in your radiator. The density tells you the concentration and how much freeze protection you have. Organizing the universe. Classification of matter.
So let's step back and look at the big picture.
Yeah.
How do we organize all this stuff?
Yeah.
Matter. And matter is just anything that has mass and takes up space, basically.
Yep, that's the definition. And matter exists in different states. Usually we talk about 3: solid, liquid, and gas. In a solid, the particles, atoms, or molecules are packed closely, often in a regular pattern. They vibrate, but they don't really move around. That's why solids have a fixed shape and volume.
Like ice.
Like ice. In a liquid, the particles are still close together, but they have enough energy to slide past each other. So liquids have a definite volume, but they take the shape of their container.
Liquid water.
Right. And in a gas, the particles are much farther apart and moving randomly at high speeds. They fill whatever container they're in, no fixed shape or volume. Steam. And changing between these states, melting ice, boiling water, that's a physical change. The substance is still water, H0, just in a different form, the molecules themselves haven't changed.
Okay, physical change is about form. So how do we classify the substances themselves?
We broadly divide matter into pure substances and mixtures. A pure substance has a fixed, constant composition. It's the same throughout. Pure substances can be either elements, the simplest building blocks, like gold, oxygen, carbon, which cannot be broken down further by chemical means.
Like the letters in our alphabet analogy.
Exactly. Or they can be compounds, which are made of two or more elements chemically bonded together in a fixed ratio, like water, H0, or salt, NaCl. Compounds can be broken down into their elements, but only through a chemical change, like running electricity through water to get hydrogen and oxygen gas. The original substance is destroyed and new ones are formed.
Okay, elements and compounds are pure substances. What about mixtures?
Mixtures have variable composition. You can mix things in different ratios. Think salt water, you can make it really salty or just a little salty. And mixtures can be homogeneous, meaning they look uniform throughout. You can't see the different parts. Air is a homogeneous mixture, mostly nitrogen and oxygen. Salt completely dissolved in water is too. We also call these solutions.
Okay, uniform, like Kool-Aid.
Right. Or they can be heterogeneous. In these, you can see the different components: sand and water, oil and vinegar dressing, concrete.
Iced tea with ice cubes floating in it.
Perfect example. You can clearly see the tea and the ice as distinct parts.
So matter breaks down into mixtures and pure substances, mixtures into homogeneous and heterogeneous, pure substances into compounds and elements. It's a nice hierarchy. The art of sorting, separation of mixtures, and if you have a mixture, you can usually separate it back into its components using physical methods, right? Since no chemical change happened to make the mixture.
That's the key idea. You exploit differences in the physical properties of the components, like filtration. If you have a solid mixed with a liquid, you pour it through filter paper. The liquid goes through, the solid stays behind. Simple.
Like making coffee.
Pretty much. Another common one is distillation. This works when components have different boiling points, different volatility. You heat the mixture. The substance with the lower boiling point turns into a gas, vaporizes first. You then channel that gas through a cool tube called a condenser, where it turns back into a liquid, and you collect it separately.
That's how you can get pure water from salt water, right? The water boils off, the salt stays behind.
Exactly. It's used widely for purification. Then there's chromatography. This is actually a whole family of techniques, but the basic idea is sex. You have a stationary phase, like a solid or a liquid coated on a solid, and a mobile phase, a liquid or gas that flows over or through the stationary phase. You put your mixture at one end, and as the mobile phase moves, the components of the mixture travel at different speeds depending on how strongly they interact with each phase.
So they separate out based on stickiness, sort of.
Sort of, yeah. Differences in affinity for the two phases. Paper chromatography, where ink separates into different colors on paper as water moves up, is a simple example you might have seen.
Right. These separation techniques are powerful. But you mentioned earlier, absolute purity isn't really achievable.
It's an ideal we strive for, but yeah. In the real world, every substance contains at least trace amounts of impurities. We talk about degrees of purity, but 100.00007% pure is generally not practical or even possible.
Good point to keep in mind. Okay, so we've covered a lot of ground, from atoms to measurements, the scientific method, classifying matter, separating mixtures.
It's the essential foundation, and honestly, understanding these basics isn't just for chemists, it sharpens your critical thinking, especially when you consider those human limitations on science we talked about and how theories evolve. It makes you think, doesn't it? When you encounter scientific information in the news, online, wherever, what's your responsibility? How do you evaluate it critically, knowing what you now know about how science works?
That is a really important question for everyone listening, something to definitely reflect on. Well, this deep dive into chemical foundations brought to you by the Last Minute Lecture team hopefully gave you a solid start. We really hope this has been useful for you. Thanks so much for tuning in and exploring these fundamental ideas with us. Keep learning.